What's up, everybody? Thank you for joining me today on another Sunday. We're about to start really soon. Just wanted to give you a heads up as to what's new and what's coming out soon on this channel. And if you're new to this Q&A, welcome. I really see that I have questions already popping up, which is awesome. So just to let you know how this works and how this goes on, basically what's going to happen is during an hour, I'm going to try to answer as many questions as possible. So if you have specific questions, that really helps me out because it makes everything kind of runs smoother. So if you have, like, let's say a homework question or some sort of actual question with numbers or something like that, something that's specific, then definitely put that in the chat. Make sure to write that out. And then I'm going to try to answer as many questions as possible, but I do want to give everybody a shot to get, their question answered. So right now, at least in the beginning, I typically just pick from, one question from each person. So that's just what I wanted to let you guys know. All right, and then another little thing real quick is that I don't know if you guys know, but I have detailed notes that I make for you guys at a very, very low price. It's basically very, very low because think of it as like a Starbucks drink or a coffee. So that's what I've been doing. I just completed redox reactions, so I recommend checking that out. It's in the description box of this video and really every single video. So yeah, all right. I am ready. So I'm ready to answer questions now. I see people already putting questions down. Let's start with the first question from Laura. And she asked, can you explain the phase diagram? Okay, so I'm going to give you a general sense of what a phase diagram is. And let's go to an actual drawing of it. Here we go. Okay, so what a phase diagram is really representing is just how we're changing our phases overall. And then what we're going to start off with, typically temperature is your x-axis and then pressure is your y. So now what we'll see is there's specific places on your phase diagram that symbolize like a specific phase. So here, let me draw this out real quick and I'll explain what everything means. Okay. So the first part here, this is going to be where it's a solid. And then next here we have a liquid. And then lastly, we have a gas at the bottom. And then what I'm talking about is really just knowing exactly what area on our graph is that specific phase. That's what you will be tested on. So next, we're also going to get into just what every little point that I've written out means. So like, let's say right here, what this point is called, it's called the triple point. So what the triple point is essentially saying is that is where all three phases exist at a given temperature and pressure. So that at that exact temperature and pressure, there's a solid, liquid, and gas existing all at once at that triple point. So that's something to definitely note. And then let's see anything else. So the main thing how to use this, think of it kind of like an X and Y coordinate or like a point that they're going to give you where, let's say if we were given that this was 100 degrees Celsius and then our pressure was, let's say, 1 atmosphere. Okay, and I'm going to say that's actually higher up. Let's say 1 atmosphere is there. So how you would read this is you would trace, or going to like the x-axis, you'd see, okay, we have 100 degrees Celsius, and then our pressure is 1 atmosphere. And if it asks you what state is it in or what phase is it in, well, it's solid. It's a solid. So that's how you would read and use this phase diagram overall. Another quick little tip before I move on to the next question is understanding what's going on as we go from a solid to a liquid or back and forth with just freezing. So if we were to go from a solid to a liquid, that would be melting. And then if we were to go backwards, going from a liquid to a solid, that would be freezing. And then if we were to keep on going with this concept where, let's say if we're now going from a liquid to a gas, that is known as vaporization. And then if we were to go backwards now, going from a gas to a liquid, that's condensation. All right, so these are really important processes to know and memorize. One more thing here. Let's say if we were going from a solid then to a gas. So going from a solid to a gas, that's known as sublimation. So sublimation. And then going backwards, going from a gas to a solid, that's deposition. So deposition, I know, I'm running out of room. There we go. Okay, so that's essentially the whole process, or the entire phase diagram explained. Definitely know these regions and how to use it. Like I said, think of it like a typical coordinate, or you're graphing a point where your X is the temperature and your Y is your pressure. Moving on to our next question. So Dylan asks, can you explain mole ratios and limiting reactants? Okay, so I'll definitely do that. I just want to make sure that you guys kind of know this as well. If you guys have a specific question, that would help a lot, just because it helps me know, what area you for sure need help with, rather than the general concept. And then I will look at other examples. It just kind of helps me with time to not have to look up all these other examples. Here, let me find an example on limiting reactants, and then mole ratios will go hand in hand with limiting reactants. So let me grab a limiting reactant question real quick. Here we go. And then I'll go from there. Let's see. Okay. So let's say if we were asked, let's start off with this first one. If we were given some sort of equation, and I'm going to balance this out real quick. So let's say we're given this equation. Let's say this is 2, this is 2, so that's balanced. And we're asked to find the limiting reactant. And let's say we're given our first reactant. We have 9.5 grams of H2 gas, and we have 1.2 grams of O2 gas. And like I said, we're asked to find the limiting reactant. So to find the limiting reactant, what a limiting reactant even is, think of it as it's the reactant that runs out the fastest. So since that's the one that's going to be used up or runs out the fastest, it's also going to produce the least amount of product. So what we're going to do with this is we're going to go from grams of our reactant to then the grams of our product, which is in this case is water. So I'm going to start off with grams of H2, and then I'm going to make my way to grams of water. Now, a lot of times, it's tricky to see, where do I even start? Where do I begin? If you don't know where to start, I recommend just changing this to moles automatically. It works every time because everything equals moles. So I'm going to go from grams of H2 to moles of H2. Then I'll do my mole to mole ratio to get to moles of a different compound, which is moles of H2O, and finally get to grams of H2O. So what you're always going to do, by the way, for a limiting reactant question, you're going to go from grams of your reactant and then make your way to grams of your product for each reactant. Okay, so let's start off. Let's start off with that 9.5 grams of H2. And then from there, I'm going to get to moles. Remember, to get to moles, we have to find the molar mass of H2. So let's find that molar mass of H2. And then note that H, or hydrogen, is really just 1.01. We're going to multiply this by 2 since there are 2 hydrogens. So in total, our molar mass is 2.02 grams per mole. That's what I'm going to use as my conversion factor. And I'll put that on the bottom to align the units so they can cancel. And on top would be 1 mole of H2. Okay. And for everybody that's joining in right now, I'm doing a limiting reactant question. So if you're struggling with that, or any stoichiometry question, that's what we're focusing on right now. Then as we go from grams and grams of H2, that's going to cancel. We're now at moles of H2. All right, so from there, I'm going to do a mole to mole ratio. You use a mole to mole ratio whenever you're trying to change the compound entirely. So since we're going from H2 to then H2O, we have to use our mole to mole ratio, which comes from our balanced equation. So the numbers that I'm going to take are just the numbers that are in front of those compounds in the balanced equation. So since there's a 2 here, then that means there's going to be 2 H2, okay? And then there's going to be 2 waters. So 2 moles of H2 and 2 moles of water is essentially what we're looking at. That's how we use a mole to mole ratio. And then now I'll place the 2 on the bottom, and that's the 2 moles of H2 that we found, and then 2 moles of H2O. Like I said, this is always from the balanced equation. And then those moles and moles of H2 would cancel. Finally, we'll get to grams of water, which is what we're looking for, so it has to be on top, and moles of H2O, which has to be on the bottom. We'll find the molar mass of H2O. So since there are 2 H2Os, or H's, this would have been 1.01 times 2. So that is 2.02, and oxygen has a molar mass of 16. I'm just using the periodic table from there. So 16 plus 2.02, that would give us 18.02 grams per mole. That's what I'm going to place on top, 18.02, and on the bottom would be 1 mole of water, and then I'm going to multiply straight across and divide by both of these multiplied. So let's see what that gives us, and then after we do that, we have to do the same thing with the other reactant. So here we'll see 9.5 times 2 times 18.02 divided by really, what, 4 point, here, let me delete that, 4.04. So that'll give us 84.75 roughly, and this is grams of water. So like I said, we have to do this same exact process with the other reactant, which was O2. So I'll start off again. We're going to go from grams of O2 to moles of O2, then to moles of the whatever compound we want, which is water, and then lastly, grams of water. So really, this is grams of reactant to grams of product. And then now I'll do 1.2 grams of O2. From there, we need the molar mass again of oxygen, or an O2 in this case. So oxygen is 16, multiply that by 2 since there's 2 of them. This would give us 32. I'll place a 32 on the bottom and then align the units so they can cancel. 1 mole will go on top. Our grams and grams would cancel. We're now at this step. So we want to go back to our balanced equation because that was our mole to mole ratio. Okay. And someone just asked, are these pre-recorded? No, because I just read the question, right? So no, they're not pre-recorded. They're live. Okay. And then now let's go back to our balanced equation to do our mole to mole ratio. So since we're doing moles of O2, there's 1 right there, okay? And then now we're trying to get, there's 1 mole of O2, and we're trying to get to water, so 2 moles of H2O. Okay, that's what I'm going to use. 1 mole of O2 and 2 moles of H2O. Let's go back. So we said 1 mole of O2 for every 2 moles of H2O. We'll bring back the molar mass of water that we found before. So I'll place 1 mole on the bottom. And then we'll also put, let me scooch this over. This would be 18.02 grams of H2O. And then now we'll just multiply straight across and divide by 32. Okay. 1.2 times 2 times 18.02 divided by 32. There we go. So this would give us 1.35 grams of H2O. Okay, so now that we see that, what we're going to do is we're going to compare each reactant and see how much did each reactant produce in product, which would be grams of H2O. So our H2 produced 84.75 grams of H2O, okay? And then our other reactant, which was the O2, produced 1.35 grams of H2O. The reactant that produces the least amount of product is your limiting reactant. So in our case, O2 is our limiting reactant because it produced the least amount of product. So that is the process that you're always going to see, by the way. You're typically going to go from grams of reactant to grams of product if they initially started or they initially gave you the grams of the reactants. If they instead gave you the moles, then you'll go from moles of your reactants to grams of your products and so on. So that's limiting reactants. Let's move on to the next question. Okay. So our next question is from Isabella, and she asked balancing equations, and you give me one to balance. Perfect. Okay, so let's write all this down. This is a combustion reaction. So right now I'm balancing a combustion reaction, and you gave me 2 to balance out. Okay. So the tricky part, I'd say, with combustion reactions, not always, but sometimes they will give us fractions. So I'll show you how to do that. Let's start off with this one. Okay, So the first thing that I always do with balancing equations is I'm going to separate all of the elements by themselves on either side and then count how many of each element there is on either side. So starting with, let's say, carbon and hydrogen and oxygen, and I'm going to mirror that on the opposite side. This is pretty much just to separate how many on the reactants do we have versus how many on the products do we have, and it helps me balance faster. So carbon has 6 due to that subscript. Hydrogen has 14 and oxygen has 2. Now look on the product side, carbon has just 1, and then oxygen has 2 here, 1 here, so really 3. And then hydrogen has 2. 2. Okay, so what I like to do is I leave hydrogen and then oxygen to the very end, since those are the ones that are trickier. I like to balance out carbon first or anything other than hydrogen and oxygen. So what I'm going to do is I'll place a 6 in front of CO2 because now that balances out the carbon. However, think of it like you're distributing, okay? Where this is where we're distributing in that 6, and now carbon has 6, and then I have to multiply this 6 times this subscript of 2 for oxygen, giving us 12, and then I'll add it to this extra one that we have, so now we have 13 oxygen. All right, and then we still have 2 hydrogen since we didn't change anything. Going from there, now I'm going to look at the hydrogen, and then we have 14 on the reactant side. We need 14 on the product side. So think of it as, what should I multiply this 2 by to get 14? We need 7. And like I said before, this is just like you're distributing. So since we're distributing that 7, there's really 14 now. And then we'll recount all of our oxygen. So there's 6 times 2, which we found was 12. And I'll add that to 7 times 1, so 7. And then we'll add these two together. Now we have 19 oxygen, but everything else is balanced. Okay, so this is a fractions question. How I knew that, by the way, is once you get down to, let's say, the carbon and the hydrogen, everything other than oxygen is balanced except for oxygen. And if oxygen is an odd number, that's where I know I have to use a fraction. And what I'm going to do is I'm going to put this 19 or whatever fraction, whatever odd number it would have been. Let's say if it was 15 or 13 or so on, you're always going to put that odd number and divide that by 2. It's always over 2. There's no exception to that. And then from there, our last step is to then get rid of that fraction. So if we want to get rid of that fraction or that denominator, what we're going to do is multiply everything by 2. And when I mean everything, I mean every single coefficient in front, not the subscripts. And then I'll distribute that in and we'll see what we get. Okay, so this would have been 2. And our first hydrocarbon, this would have been 1902. And then now, and because those 2's would cancel, by the way, and then now we'll multiply again. 2 times 6 would be 12, and then we'll get 14 waters. That is the balanced equation. Okay, and then, where was I? Okay, next one. Can you help me on, Luisa says, can you help me on molar mass of a gas and Dalton's law? Okay, here we go. Let me find an example for you. So whenever we're doing molar mass of a gas, we're going to be using the ideal gas law, which is PV equals nRT. And then let me find an example for Dalton's law as well as everything else. Where do I have my gas laws? Let's see. Okay. All right, let me find one. This is molar mass of a gas, so I just want to have a specific type. Oh, I had one. Let's rate of fusion. There we go. Here's one. Okay. So let's say if we had, I'm just going to state everything that we're given and then what we're finding. So let's say they gave us a mass of 0.311 grams and then a volume of 0.225 liters, a temperature of 55 degrees Celsius, and then a pressure of 886 millimeters mercury. All right. And then we're asked to find the molar mass. So just to remind you, molar mass is referring to grams divided by moles, okay? So let's go back to what we're given, and we're already given that grams portion, so this first part is done. There's no need to do anything with that grams. You don't have to change it to moles. Instead, what we're going to do is with all the other information that we have, we're going to plug this in to PV equals nRT, and the only thing that we don't have is then the moles. So we're going to find the moles, and then at the very end, we're going to divide the grams that was initially given by the moles that we found using the ideal gas law, or PV equals nRT. Okay, so that's the whole process. That's what you're always going to really do whenever you're asked to find molar mass, typically for these types of questions. The first thing, though, that I want to do is convert all of my units into the proper units. Whenever we have the ideal gas law, we want our pressure to be in atmospheres, our volume to be in liters, and of course is moles. And then temperature has to be in Kelvin. So for all gas laws, by the way, temperature has to be in Kelvin. And then lastly, R is just a gas constant, which is 0.0821 liters times atmospheres divided by moles Kelvin. Okay, so let's just start off with converting all of our units. I'll start off with temperature. Since volume is okay, it's in liters, it's happy. So I'm going to add 273. This is how we convert from Celsius to Kelvin. So adding that, let's see what we get. 328 Kelvin. And then next, for pressure, it's known that 1 atmosphere is equal to 760 millimeters mercury. So that I'm going to use that as my conversion factor. So I'll divide this by 760 millimeters mercury, and that's per every 1 atmosphere, and that'll give me my pressure in atmospheres. And I'll put that down here. So that would give us 1.1657 atmospheres. And then what I'm looking at is I typically have a huge packet of examples and everything laid out. It just helps me teach. That's what I've kind of made, and that's what I do with my notes, by the way. It's just really helpful to show that to you guys later on, and that's how I'm building all my notes for you guys. And let's plug everything in. Okay. So what I like to do is to rewrite this formula already solved for whatever I'm looking for. So since I'm looking for moles, I'm going to divide over RT to both sides. And then this RT would then cancel. And now our new formula is N is equals to PV divided by RT. Now I'll just plug in and solve. So we said our pressure that we found was 1.1657 atmospheres times the volume that was initially given, which is 0.225 liters. And then we'll divide that by our gas constant. And then I'll show you how everything cancels out. That's why we specifically want everything in those units that I mentioned. And then now our temperature was 328 Kelvin. So just looking at the units, our atmospheres cancel, our liters and liters cancel, our Kelvin and Kelvin cancel, and we're left with moles, which is exactly what we're solving for. So yeah, that's so far so good. And then we'll multiply straight across. So multiply these two and divide by these two. So that'll give us 0.00974 moles. Okay, so from here, we found our moles. Now let's go back. So let's go back to what we were given. So we found this part. We found the moles on the bottom. We were given the grams initially in the question. And then now all I have to do is divide, and that's my molar mass, and we're done. So a lot of times with these questions, it's units that is the main thing that I think can be tricky. It's just making sure everything is in the proper units and then going from there. So going from here, let's figure out what our molar mass is. So really mm just means molar mass. And then I'll place that moles on the bottom. And then on top will be our grams that we were initially given, which was 0.311 grams. And lastly, our molar mass after we divide would have been 31.92 grams per mole. And I'm going to double check my sig fig count going back to the initial given. Everything initially given would have been 2 sig figs actually. So I'll round this to 32 grams per mole. And then that is my final answer. So that would be for molar mass for Dalton's law. That's a bit different. I'll see if I can answer that. But like I said, guys, if you guys have specific questions, that helps me a lot, just because there is so much to one specific topic. I'll go over what Dalton's law is real quick. Where do I have my partial pressure? So Dalton's law of partial pressures is essentially saying, I'll kind of give you an overview of everything. I wanted an example. If I don't have it, I don't think I do. Shocking. Okay. All right. So I'll give you an overview of what Dalton's law is essentially talking about. So let's say if we have a container. Okay, so Dalton's law is about partial pressures, and essentially let's look at all these different gases in a closed container. So let's say if I had neon gas, hydrogen gas, and let's say oxygen gas, sure, all together. Okay, so if everything is all together, and if I were looking for something known as the total pressure of this container or of this gas mixture, what I would do is I would add each individual gas's partial pressure, or think of it as each individual gas's pressure, okay? So from here, this is going to be the partial pressure of H2 plus the partial pressure of neon plus the partial pressure of O2. So that's what you would do whenever you're finding your partial pressure, or really your total pressure of that mixture, that gas mixture. That's essentially the concept behind it. Real quick, if you were to try to figure out what your partial pressure is of a specific gas, what this would have been is something known as your mole fraction times your total pressure. And then lastly, so pretty much right now, I'm just giving you the formulas and what you would do. What a mole fraction is, it's the moles of whatever you're looking for divided by the total moles. So in this case, it would have been the moles of H2 plus the moles of O2 plus the moles of neon, and then that would have been your total moles. And after you found this number, by the way, this is unitless. Mole fractions, moles cancel out, so it's unitless. Like let's say if this gave you 0.4, then that's what you would plug in here. And then if they initially gave you the total pressure was, let's say, I'm going to say 1 atmosphere, okay? So let's say then I'll plug that in there, and then that would have given me my partial pressure of H2. So that's essentially the main thing. Like I said, there are a lot of different ways they can word this question, but that's the general overview of what I've typically seen. Okay, so let's move on. Liz asks, what is theoretical yield? Great question. So your theoretical yield is whatever your limiting reactant produces. So previously I answered, I believe, Dylan's question that asked about limiting reactants. And what I did was I went from grams of, so you can rewatch, like in the beginning, you can rewatch this once it's done, but this would have been grams of, let me give you a quick little example to explain this further. Here we go. Balance this real quick. Okay. So let's say if we did this previously, and if I was given a certain amount of H2 and a certain amount of, I don't remember what I said before. Let's say it was something like this, grams of O2. Okay. So if we first find our limiting reactant, which is the reactant that is used up the fastest, as well as, think of it as whatever, your limiting reactant is going to produce the least amount of product, okay? That's what I want you to focus on. So what we found was that O2 produced the least amount of product. So whatever, since this is our limiting reactant, whatever our limiting reactant then produced, so let's say this ended up giving us 1.3 grams of H2O, then this portion is our theoretical yield. And then, by the way, theoretical yield is always found by stoichiometry. What I mean by that is, let's say if I started off at 1.4 grams of O2, I would then make my way from grams of O2 to moles of O2. This is all stoichiometry, then going to moles of H2O, which is our product. And then lastly, to grams of H2O. So as I, did that, this being the molar mass and so on, then whatever I ended up at the end, here, I'll do it real quick. So whatever I ended up at the end, this is O2, this is 2. And then this was 18.02. Okay. Whatever value I get, that is then going to be my theoretical yield. Like I said, it's whatever your limiting reactant produces. Okay. Hope that makes more sense. Definitely go. I have a video on it, by the way. I have a limiting reactant video that I gave a really good visual on it. So that can also help you with limiting reactants and theoretical yield. Plus, I also have really, really detailed notes that I currently have up and running. I recommend checking that out. It has pretty much as many possible questions on theoretical yield, limiting reactants, excess reactants, and everything on this topic. So I'll be placing a link right now in the chat, and it's also in my description. Okay, so definitely check that out for people who are struggling with limiting reactants. I have notes on that. I also have notes on a lot of things, molarity and redox reactions and so on. So check that out. I have a question. Do you really have to draw lines? I could do that faster without them. Great. That's really up to everybody. So yeah, so it's up to you. You know, I personally like to have it a little bit organized, but everybody learns differently. So whatever works for you. All right, let's move on. All right, so Brittany asked, how do you go from mole ratio to build a formula? All right, so CuClH2O. How do you go from... Brittany, are you stating mole ratio to build a formula? I believe you're asking empirical formulas and molecular formulas. Is that what you're asking? Or are you kind of just want to clarify on what your question is asking? So I'll skip it for now. Please let me know, Brittany, and then I'll go back to yours. But like I said, let me know if it's empirical formula or... yeah, let me know exactly what you mean by that. Oh, it is. Okay. Okay. Got it. So if we were going to, there's a lot more that we need for this, but here. So how do you go from mole ratio to build a formula? I'm going to give you another example just because you need to be given a certain amount for every single element. Okay. So I'm going to give you an example with that. And let me find that for you. Doing an example of that right now. Let me just find empirical and molecular formulas and go from there. So I'll start off with something. We're actually going to do both. So to find your molecular formula, you have to figure out your empirical formula. Okay, so let's say if we initially were given 74.02 grams of carbon and 8.710 grams of hydrogen and 17.27 grams of nitrogen. And then we also were given that the molar mass of our total sample or whatever we're asked to find is 162.3 grams per mole. So this is the information that we need to be given to, to do something about it. So to find our molecular formula in this case. So what I'm going to start off doing is just finding the empirical formula. And then real quick, something to note is if instead of grams, if they gave me a percent, then I could automatically just change this percent to grams. If, of course, this is out of 100%, you could always check that by adding up all of the percentages that they give you. So that's something to kind of, to look at. So instantly we could have just changed this grams or this percentage to grams without any calculation. So just a little note of that. Then once we have it in grams, the next step is to convert every single grams into our moles. Okay. So looking at grams of carbon, I'm going to convert that to moles. And then let's find the molar mass of each. So then we know, just looking at the periodic table, this is 12.01 grams of carbon per every 1 mole of carbon. And then from here, I'll just divide. So dividing, this would have been 74.02 divided by 12.01. And then this is 6.16 roughly moles of carbon. I'll do the same thing with everything else, just converting them to moles is our first step. And then this would have been 1.01 for hydrogen, just the molar mass of hydrogen, and then on top 1 mole. and then we'll divide. So 8.710 divided by 1.01. This gives us 8.624 moles of hydrogen. And lastly, I'm going to do the same exact thing for nitrogen. So dividing by the molar mass, that would have been 14.01 grams of nitrogen per every 1 mole of nitrogen. And then after that, after we've divided, that gives us 1.233 moles of nitrogen. Now that we have everything in moles, we're then going to divide by the least amount of moles. So our least amount of moles is the nitrogen. I'll divide everything by 1.233. And then right there, what this gives us the subscript of our empirical formula, or for our empirical formula. So dividing all this, by the way, you can round. I'll tell you exactly how to round. But after we are given this would have given us 4.998. So that is okay to round to 5. And then the next one would have given us 6.99. That's okay to round to 7. And then this last one would just gives us 1. Okay, so real quick, if you didn't have this like nice 4.99, or it wasn't, really, really close, okay, then what it would be is, let's say if this instead ended up as 4.5, then you would multiply each one of these subscripts by 2, just to make it a whole number. And then so on. If you were given, let's say this was 4.33, so it ends in 0.33, or it ends in 4.66, or really just 66, okay? Then you would multiply by 3 to every single subscript again. And lastly, if this ended in 0.25 or in 0.75, then you would multiply by 4 to every subscript. Just little side note, just in case you get that. And then now, since we don't necessarily need that, I'm just going to write the empirical formula, then we'll get to the molecular. So our empirical formula would have been carbon has a 5 subscript, and then hydrogen has a 7, nitrogen has a 1. This is our empirical, okay? So this is our empirical formula. That's how you find an empirical formula. Now, let's figure out how to find our molecular formula. What you're going to do is you're going to find the molar mass of the empirical formula that we just found. So let's do that. So carbon has a mass of 12.01, and there's 5 of them, so I'll multiply by 5. And then hydrogen, there's 1.01 molar mass times 7. And then next, nitrogen, there's just 1. So that's 14.01. Then after that, let's add everything up. Let's see what that gives us for our molar mass. So I really have these done. This would have been 81.13 grams per mole. So that's just for our empirical formula. The next step, we're almost done. The next step is to divide your molecular molar mass that was initially given, which is always initially given and has to be given, by the way, to find your molecular formula. So your molecular formula is molar mass on top divided by the empirical formula's molar mass. I'm just going to put mm. So what I want you, or how you remember this, by the way, how I would always remember this, is don't forget about me. So molecular formula's mass divided by the empirical formula's molar mass, and then let's plug everything in. Okay. So on top would be what was initially given, which was 162.3, and then on the bottom would be that 81.13 that we found previously. After you divide those two, this would just give us a whole number of 2. What we're going to do with that 2, let's go back to the empirical formula, and you're going to multiply that 2 to all of your subscripts, and then this will finally give you your molecular formula. So our final answer, our final molecular formula would be C10H14N2. Okay, that would be our answer for that. Definitely check out other videos. I actually have 2 videos. I believe I even have this question on there. One showing you empirical formulas and another video showing you molecular formulas. So check that out. Okay, let's move on to another question as I take a quick sip of water. Okay, Belinda states, can you help explain redox and oxidation and reduction, how to define which compound does what? Sure. Okay, so let me give you a general question with that. And then, by the way, if you, of course, need more help with that, I do recommend checking out my notes. I have, I just posted redox reactions that are very, very helpful. So, okay, let's find redox reactions. All right. So a big thing with redox reactions is always finding just what your oxidation numbers are, okay? And let me actually find better redox reaction questions because I didn't like this one that I have. Okay. Your oxidation numbers are extremely important because they help you figure out where to start, okay? So let's start off with, let me find one. That one's fine. Okay. Let's say if we're given this balanced equation, and I'll help you figure everything out. All right, so let's say if we're given this, the first step, and always the first step, is to figure out your oxidation numbers. So first things first, whenever you see one element, and just one element in its solid state, it will have an oxidation number of 0. Now, moving on to something that is diatomic. A diatomic atom pretty much is, it exists in pairs. So like O2, H2, C2, F2, and so on. So, and whenever it's a gas, that also kind of hints that it's going to be diatomic. Now, that's also an oxidation number of 0. Now, continuing on to something that is a compound. So whenever oxygen is within a compound, it's going to have an oxidation number of -2. Now we have to figure out what is the oxidation number of magnesium. So looking at magnesium, this is all going to equal the entire charge of this compound, which is, it's neutral, meaning there is no charge, it's just 0. So let's say if I don't know what that is, that would have been an X, and then we do a little bit of math, add that over, so X is then equal to a +2. Okay, so you could have seen that here, but there are some ones that are trickier to see. I typically like to write an expression or an equation just to help you guys out. So then those will act as our oxidation numbers, everything that I've written out here. Now, what I like to look at it, or how I like to look at it, is oxidation, looking at our oxidation numbers, that's going to go, or really become more positive, okay? So oxidation becomes more positive when it comes to our oxidation numbers. So which one became more positive? The magnesium. So that would have been oxidation. So like I said, oxidation becomes more positive when it comes to oxidation numbers. And the reason why it's doing this is because oxidation is a loss of electrons. So what I like to think of it is, as you lose negative thoughts from your mind, you become more positive, okay? So that's kind of, I know it's like backwards as to how you're thinking, but that's something that I like to kind of focus on, or how I remember it. So that's why it's becoming more positive. And then reduction is then going to become more negative. So going from, or looking at oxygen, this is reduction because our oxidation numbers became more negative. And essentially going back to that same little, concept, think of it as, you could also think of it as you gain negative thoughts in your mind, you become more negative. Okay. So that's something else. I'm seeing other people say oil rig. Yep. Oil rig's another one. Leo, the lion goes grr. That's another one. You might have heard that, but I typically just prefer saying oxidation. It's the one that becomes more positive, and then reduction becomes more negative with oxidation numbers, just as help my students. And I personally like it that way, but whatever works. So then what else? And then how to define which compound is what. Got it. Okay, so last thing for this question is, if we were asked which substance, which element is being oxidized, which one's being reduced, and what's your oxidizing agent, what's your reducing agent. So whatever we're looking at, whenever we're looking at something that's being oxidized, reduced, or what's our reducing agent, oxidizing agent, we're only going to focus on the reactants, because that's what's doing that, that's what's being oxidized. It's never going to be the product. That's just something to note. So whatever is being oxidized, it's the reactant that is involved in oxidation. So which one is that? Well, that would have been magnesium. So magnesium in its solid state would have been oxidized. And then what is being reduced is the reactant that is undergoing reduction. So that would have been O2 gas. And now let's go back to what's our oxidizing agent, what's our reducing agent? Well, whatever is being oxidized is known as our reducing agent. So they're backwards. Okay, so this would have been our reducing agent. And then here, this would have been our oxidizing agent. And oxidizing agents are whatever is being reduced. All right, so that's everything on your question. So let's see what else we have with my time. Yeah. All right, Emily asks, a piece of solid metal, copper metal, is put in an aqueous solution of magnesium sulfate. Write the net ionic equation for any single replacement redox reaction that may be predicted. Okay, so let's see what we got. We have to build this overall. So we have copper metal so copper, it's in its solid state. That is going into aqueous solution of magnesium sulfate, and I'm going to look back at my activity series since this is going back. Here we go. Okay, we're going from copper to magnesium sulfate, and that's aqueous. And we're trying to see, will this produce, write the net ionic. Okay, write the net ionic, got it. So we're going from copper to magnesium. Okay. So looking at something like this, copper typically has, let's go to our charges. They don't tell me what it was, do they? No, it does not. I'll state that it's 1. However, let me see what they might have wanted. One sec, just double checking one thing. Whenever we have single replacement reactions, a lot of times there is a possibility that there will be no reaction. That is dependent on something known as the activity series. So I'm just checking for that at the moment. Okay, as I keep going. All right, 2+. Yeah, that's what I thought. Okay. So we're good. I'm going to keep going with this. And then Belinda says, thank you. You're welcome. Happy to help. And then KP says, how do you determine which is the spectator ion in questions like these? Sure. So the spectator ions are whatever cancels out. And I'll show you that right now. So let's just, first off, let's figure out what our products are, balance this out if it needs balancing, and then I'll show you how to find everything. So what's going to happen with this single replacement reaction is that this copper and magnesium are essentially going to just switch. And then what will happen is copper will now combine with that SO4, and then magnesium will be left on its own. So this is now plus just magnesium is on its own. Copper is most likely going to have a 2+ charge, and sulfate has a 2- charge, so it's balanced. So I'm not even going to put the charges, just showing you that that was neutral. There's no need for subscripts, and everything else is completely balanced. Now, how we're going to figure out, what else we produce or what we have is going back to solubility table, which I'm going to grab right now. But our solubility table is essentially going to tell us if something is aqueous or not, or a solid, really. So how I use a solubility table to predict my products is I look at the ending. So looking at SO4, sulfates are typically soluble. So since they're typically soluble, that essentially means that it's going to be aqueous. So soluble means aqueous, insoluble means a solid. And then now let's look at any exceptions to the rules. So sulfate is typically soluble with the exception of silver, calcium, lead, and several others that aren't copper. So this is going to be aqueous. It is extremely important to know what will be aqueous and what will not, because that's going to tell us what to separate. Remember, we only separate out our aqueous solutions, nothing else. Okay. And then now let's go from there. Magnesium would also be in its solid state. Okay, because it's by itself and it is a type of metal. Okay, so what we'll do now is really just separate all of our aqueous solutions. So I'm going to leave copper alone. And then now I'm going to separate out our aqueous solutions into separate ions and putting the charges. So magnesium will be on its own with a charge of 2+, and then I'll state that it is its aqueous state, and then sulfate, SO4 2- in its aqueous state. And then we'll keep going. We'll also separate out this other aqueous solution. So this would have been copper with A2 plus charge, that's aqueous, plus sulfate 2 minus, also aqueous, and I'll leave magnesium alone since it is in its solid state. And then from here, how we're going to identify our spectator ions is whatever we see is the same. And make sure to include those states because those states also have to be the same. So our spectator ions are whatever that we have on the same reactants and on the products. So meaning, let's look at sulfate. SO4 2 minus. Those would cancel. Those would be our spectator ions because they're exactly the same on either side. So that's one of them, and that's actually all we can cancel out since copper is not charged. So it's not the same on either side. Same thing goes for magnesium. They're not the same. Instead, what we'll do now is rewrite this entire formula. And then I'm just putting the states again. And that's why they stated anything that is a redox, or yeah, rewrite this as a redox reaction that may be predicted correct. So this is a redox reaction. A lot of times how I can just tell is whenever we have that same element starting off as neutral and then going to something being charged. Okay, so that's something that I typically just see and can tell it's a redox reaction, but that would be our answer for that one. And I'll move on to more solubility. Okay, hope that helped already, Max, but I'll go back into it. So Max asks, can you explain solubility? I understand that you need to look at the table to figure it out, but I don't find that very helpful. I think this goes hand in hand with precipitation and aqueous reactions. Yes, it does. Okay, so let's see how I can write this real quick. But how we use a solubility table overall, I'll draw something out just to show you a general gist of what everything looks like. But essentially what they're going to state is they're going to have two different sides, or some people literally just list all of the different types of like what can be soluble, what's insoluble. But this is how I look at it. So if we know something is soluble, we know that that could have been in group 1. So let's say lithium or sodium, and then they're always going to give you exceptions to that rule. So essentially, the first column is telling us that that's what's soluble. So that's aqueous. Okay, so soluble means aqueous. And then if they're giving us exceptions to that rule, that means that's where it's a solid or insoluble. And then from here, they're pretty much just going to tell you and identify, are there any exceptions to that rule? So no, not in that first case. Group 1 will always be aqueous or always be soluble. And then same thing with NH4+, this is ammonium. That's typically soluble. There are no exceptions to that rule, and so on. Then we'll keep going, and anything like, let's say, nitrate, that's also always soluble. There's no exception to that rule. And they keep giving you other ones, and this is essentially what they're trying to state. I've never really liked how they have built the solubility tables. I'm actually working on making my own, but that's something that this is essentially what it's talking about. Okay, so these are just common cases that I've seen. I'm going to get down to something that does have an exception. So let's say something known as a halide. That is just talking about a halogen. Okay, some sort of halogen, but really they're referring to the ion. So that has an exception whenever it's combined with, let's say, mercury or lead or silver. That will be a solid. So for example, if we were to have KCl versus, let's say, silver chloride, okay? Looking at this first part, anything that's a halide, so I typically look at the ending, okay? I typically look at the ending where I know that's chlorine or that's a halide. So it's typically soluble, making it aqueous, with the exception of these three. So for this first one, this would have been aqueous because we know potassium is in the first group, and that wasn't part of one of our exceptions. So right then and there, I knew that's aqueous. However, looking at this second part, this is going to be a solid because, yes, it does have that exception, making it a solid. So typically chlorine is soluble. However, whenever we add these three different elements or metals, then that would make it solid or insoluble. That's essentially the concept of these types. I hope that makes more sense. Definitely check out, I have another video It's a previous live tutoring session that I did on solubility. So I definitely recommend checking that out on my videos. And I even have a solubility table that I place there that I explain even further with more details. So check that out. But that's essentially the concept of it. And then if you guys haven't yet signed up for being a part of my community, essentially what that is, it's my way of being able to help you guys and send you guys more resources. So when you sign up, and by the way, the link is in the description box of this current video and every single video. When you sign up, you receive a formula sheet of all of the different formulas that you need to know for the first half of chemistry, which I personally find really helpful just because, I mean, I hate flipping through my entire book, right? When you're just looking for one formula. And then I do plan on making other like solubility tables or other charts or resources that can really help you guys out. So definitely check that out. I am currently working on a periodic table as well as a solubility table to make for you guys. And let's move on to possibly the last question. Let's see what we got. Okay, Morgan, can you do a video explaining their thermochemistry? I could explain this question right now. And I do have a specific one on calorimetry of the, what was it? The coffee cup calorimetry question. So that I do have already, if you haven't seen that one. But this time we're doing a bomb calorimeter. Okay, let me grab my formulas because we're going to need several. And then we'll go from there. And that's over here. Okay, I have my formulas and let's write this down. So we're given 0.0100 moles of butane, and then we're asked, was burned in a bomb calorimeter. The heat from the reaction raised the temperature of 1.00 kilograms of water, and this is a butane, of water by 6.90 degrees Celsius. How much heat was released? Okay, so we're finding heat. In this reaction per mole of butane combusted, the specific heat of water, yeah. Okay, and this froze on me, darn it. I wrote everything down, okay. The specific heat of water is, let me rewrite this down real quick. So we're given moles of butane, and then we're given the heat from the reaction raised 1.00 kilo. We're given the mass of water that we'll have to convert, and then we're given temperature, so 6.90 degrees Celsius. We'll have to convert that. Actually, no, we don't. Not for this type. And then how much heat is released. So we're looking for Q. Since they're telling us that heat is being released, that's essentially stating that it's negative. Just to let you know, whenever heat is being absorbed, that's telling us that it's positive. And then now one more thing, specific heat. Okay, so our specific heat of water is 4.184 joules. All right, and it should have been joules per Celsius. Okay, so let's see what we're gonna do. We need that of our calorimeter. So whenever we're asked to do a bomb calorimetry question, there are a lot of little things, okay? So typically the equations that you're gonna see is Q of your calorimeter is then gonna equal the specific heat of your calorimeter times the change in temperature. And then since we're finding, this is specifically though, actually this isn't asking for energy, so I don't even need to put the rest of it, so that's awesome. Let me see what else I'm given. The heat from the reaction raised the temperature. How much heat was released in this reaction? It was burned in a bomb calorimeter. I'm going to divide that at the end by moles. It's asking how much heat was released rather than how much, what's our energy change? Okay, I'll go from there. So I'm just going to plug in for right now. What I'm looking at, just because it's a little bit mixed with our Q of our reaction is equal to the negative Q of our calorimeter. However, it's not asking for the calorimeter. What I'm debating on, just because it did state bomb calorimeter, but then it doesn't give me anything on the calorimeter, which is strange. The heat from the reaction raised to this is this thing. So Q of our reaction is equal to the negative Q of our calorimeter. Essentially what that's talking about is, let's say if I have You might have seen this as like a styrofoam cup, where here we have water. Let's say this is our reaction. They're always going to be opposite to each other. So as let's say the reaction is being, is absorbing that heat, then that means our overall calorimeter, which is on the outside, is then releasing that heat into, or I wouldn't even say this, is then releasing that heat into that reaction. So they're always going to be opposites. That's what we look at here. So I'll start off with just figuring out the Q of our reaction. Q of our reaction is a different formula. It's that MCAT formula. So here, we're given our mass of water, and then, yep, that's what I'll start off with. So I'm going to say Q of our reaction, which in this case, specifically, I'll state water because that's all the information they're giving me. So I'll start off with 1.00 kilograms of H2O. However, I want this in grams, so I'll convert this real quick. So 1 kilogram is equal to 10 to the positive third grams of H2O. Essentially, I'm just multiplying by 1,000. So this is 1,000 grams of H2O. And then that's the M portion of this MCAT. So I'll place that here. And then I don't need H2O. Everything is going to be of H2O. That's why they also give you the specific heat capacity of water. So this is that's the C part. So 4.184 joules per Celsius. And this actually should have been joules per gram Celsius because all of that's going to cancel and just leave joules. Now, the last thing is they gave us our change in temperature already in Celsius, which is fine. This is 6.90 Celsius. So our Celsius would cancel and our grams and grams would cancel. And then let me figure out what this gives us. So this would have been Q of our water is equal to, and we're not done just yet. So let's see what this gives us. 1,000 times 4.184 times 6.90. So that would have been 28869.6 joules. Typically they like it in kilojoules, but I'll keep going real quick. Let me see what else this question was asking, because this is asking how much heat was released in this reaction per mole of our combustion. The last thing is just to simply divide by the amount of moles of butane. However, of that, I'm trying to see what else I need from this sample. A 0.011 mole sample of butane was burned in that. However, that's the Q of our reaction. It is being released, so it would have been negative. So that would have been, yep. So what I'm thinking is Q of our water, this is essentially part of that Q of our reaction, is going to be equal to the negative Q of our calorimeter. So it would have been a negative. And then a lot of times when they're telling us that it's released, as I mentioned, it tells us that our change or our heat is going to be negative since we're releasing it. So then that's what makes it negative. And our last step is, since they want it per moles, I'm just going to divide by the amount of moles of butane that they provided me initially. So that would have been 0.0100 moles of butane. Divide that. Now you get moles or joules per mole, and we should be done. And that gives us a rather large number. So 2886960. One more thing that I will do, just because I see this all the time. They typically prefer it in kilojoules. So I'm going to convert this to kilojoules real quick just to make this nicer. So then, and this is per mole. So then now I have 10 to the third joules, which is essentially 1,000 per every 1 kilojoule. I'm just dividing by 1,000 really. And then this would give me negative 2886.96 kilojoules per mole. And that would be my final answer. One little note though, just I'd say double check this, but sometimes if like this were a homework question, like either mastering chemistry or sapling or something like that, what I've often seen them do is sometimes they don't include that negative because they've already stated that heat is being released. So it really depends on the program, unfortunately. I would double check with your teacher what she prefers, but at least on exams, I've seen whenever they say heat is released, you do put that Q as negative, but then on like mastering chemistry and sapling, for some reason, you don't because they've really stated it was released. I don't know why they do that, but just double check with your instructor with that little part, but everything else is fine. All right, guys. So unfortunately, that is all my time currently. I try to squeeze in an hour before I go to work. So I have to actually go and go back to my full-time job. So yeah, so I tutor a lot, and I make time. This 1 hour I dedicate to you guys. So I answered as much as I possibly can. But I do this every single Sunday at the same time. So if you didn't get your question answered, I do recommend coming to next Sundays as well as just being on time. That can really make sure to get your question answered. And like I said, I try to answer at least one question from each person to be as fair as possible. So thank you for being here. And hopefully I'll see you next Sunday. And like I said, if you haven't checked out the notes that I've done, they're extremely detailed. And if you're struggling, how I like to kind of look at this, it's a lot cheaper than a tutoring session. I know I am a private tutor, so I wanted to make education a lot more affordable. And then that's also why I'm doing an hour at least every week to help you guys out, because I understand what it's like being a college student or, you know, even in high school, not being able to have those resources available to me. So definitely check that out. It's in the description box. And I hope to see you guys next Sunday. Have an awesome Sunday. See you guys later.